Hi guys, this is AS Chemistry, Combustion of Hydrocarbons, question 22. Which fuel would produce the largest mass of carbon dioxide when 10 kg of fuel undergoes complete combustion? So the first thing we need to do is calculate the MR values for all of these fuels. So for biodiesel, the MR value is calculated to be 270. For ethanol, it is 46. For octane, it is 114. And for propane, it is 44. The next thing we need to see is how much of CO2 is produced by each of these fuels. So with biodiesel, there are 17 carbon atoms, so 17 CO2 are produced. With ethanol, it would be 2 moles of CO2. With octane, it would be 8 moles of CO2. And with propane, it would be 3 moles of CO2. So this completes step one. Step two requires us to calculate the moles of the fuel. So for biodiesel, since the masses for each fuel would remain the same, which is 10 kg, so this would become 10 upon 270, which gives us a mole value of 0.037. For ethanol, it would be 10 upon 46, which would give us a mole value of 0.217. For octane, it would be 10 upon 114. This gives us a mole value of 0.0877. And for propane, it would be 10 upon 44, which gives us a mole value of 0.227. So now we have the mole of each of the fuels that are supposed to be the correct option here. The correct option would be the one that produces the maximum amount of CO2. So now, once we have these values, now we multiply this by the moles of carbon dioxide, which is in the case of biodiesel 17 into 0.037. This gives us moles of carbon dioxide to be 0.63 moles. For ethanol, it would be 2 into 0.217. This gives us a mole value of 0.435 moles of carbon dioxide. With octane, it would be 8 into 0.0877, which gives us a mole value of 0.702 moles of carbon dioxide produced. And with propane, it would be 3 into 0.227. This gives us a mole value of 0.682 moles of carbon dioxide produced. So out of the four calculated values, the one with the highest mole of CO2 is octane, making option C the correct option for this question. Question 23. Compound J burns in excess of oxygen to give carbon dioxide and water only. When 3 grams sample of compound J is burnt in excess of oxygen, 4.4 grams of carbon dioxide and 1.8 grams of water are formed. What is the empirical formula of J? So when CO2 and H2 are produced, the moles of CO2 would be X moles of CO2 and the moles of H2O would be Y upon 2 moles of H2O, because these are the moles produced when a hydrocarbon is completely burnt in oxygen. So mass of CO2 is 4.4 grams, mass of water is 1.8 grams. So we divide the mass by the MR value. MR of carbon dioxide is 44, MR of water is 18. This gives us a mole ratio of 0.1 and 0.1, which means the molar ratio of carbon dioxide to water is 1 is to 1. Now here the value of X is 1 and the value of Y upon 2 is 1 as well. So if Y upon 2 is 1, Y would be equal to 2. So the empirical formula of this hydrocarbon is CH2, but we are unsure whether oxygen is part of the empirical formula or not. But since we've got at least one carbon and two hydrogen present, The options that are eliminated are options B and option A, because they do not contain two atoms of hydrogen as the empirical formula. Now, with C and D, one by one, we've got to find out which is the correct option here. So, what we do is if we take CH2 and we burn it in oxygen, so CH2 plus 1.5 O2 gives CO2 and H2O. This is the combustion equation. The next thing we need to do is calculate the moles of CO2 and H2O and multiply that by the MR to find out the mass. So the mass of the sample of compound given is 3 grams. So 3 upon MR, 12 plus 2 is 14. 3 upon 14 gives us 0.214 moles. So moles of CO2 would be 0.214 and moles of H2O would be 0.214. Now we multiply 0.214 by the MR of CO2, which is 44. This gives us a mass value of 9.43 grams. And we multiply 0.214 moles of water with its MR, which is 18, which gives us a value of 3.86 grams. According to this question, the mass of carbon dioxide is supposed to be 4.4 and the mass of water is supposed to be 1.8. So that actually eliminates option C. So option D has to be the correct option. But we will calculate the masses of CO2 and H2O to make sure that this is the correct option. So when we burn CH2O in oxygen, we only need 1 mole of oxygen. This produces 1 mole of CO2 and it produces 1 mole of H2O. So the mass given in the question is 3 grams. So 3 upon MR would be 12 plus 2 plus 16, which is 30. So 3 upon 30 is 0.1 moles, which means moles of CO2 is 0.1 and moles of H2O is 0.1. When we multiply moles of CO2 0.1 into 44, we end up with 4.4 grams. And when we multiply moles of H2O 0.1 by 18, we end up with 1.8 grams. As given in the question, mass of CO2 is supposed to be 4.4 and mass of H2O is supposed to be 1.80, which makes option D the correct option for this question. Question 24. A 0.216 gram sample of an aluminum compound X reacts with an excess of water to produce a single hydrocarbon gas. This gas burns completely in O2 to form H2O and CO2 only. The volume of CO2 at room temperature and pressure is 108 cm cube. What is the formula of X? So in order to find out the formula of X, we need to calculate two things. The first thing is the moles of CO2, which would be 108 divided by 24,000. This gives us a mole value of 0.0045 moles of CO2. The next thing that we need to calculate are the MR of the aluminum carbides. So Al has an AR value of 27 and carbon has an AR value of 12. So calculating the MR for option A, the MR is 90. For option B, the MR is 105. For option C, the MR is 129. And for option D, the MR is 144. So this completes the initial calculations required. Now, for options A to D, the moles of carbon dioxide produced depends on the number of carbon atoms present. So in the case of A, there are 3 carbon atoms present, so 3 moles of CO2 would be produced. For option B, there are 2 carbon atoms present, so 2 moles of CO2 would be produced. For option C, there are 4 carbon atoms present, so 4 moles of CO2 would be produced. And for option D, there are 3 carbon atoms, so 3 moles of CO2 would be produced. Now, let's calculate the moles of the aluminum carbide. So for option A, it would be the mass given and the question is 0.216. So it would be 0.216 divided by MR, which is 90. This gives us a mole value of 0.0024. 0.0024 moles. For option B, it would be 0.216 divided by 105, which gives us a mole value of 0.00206. For option C, we have 0.216 divided by 129. This gives us a mole value of 0.00167 moles. And for option D, we've got 0.216 divided by 129. Oh, not 129. In this case, it is 144, the MR. 129 was the MR of the compound in option C. So here we have 144 as the MR. So this gives us a mole value of 0.0015 moles. So once we have obtained the moles of each compound, now we multiply that mole by 3 or 2 or 4 or 3, which is the molar ratio of the carbon dioxide. And this value, if it is equal to 0.0045, which was the calculated moles of CO2, then that compound would be the correct compound and the correct answer for this question. So for option A, it would be 3 into 0.0045, giving us a value of 0.0072. 0.0024, not 4524. That's how we get 72. 0.0024. So 0.0072. This option is incorrect. Option B, 2 into 0.00206, which gives us 0.002 to the 412. 412, which is also not correct. Option C gives us 4 into 0.00167, and the moles of carbon dioxide calculated here become 0.00698, which is also incorrect. So for the last one, we have 3 into 0.0015, which gives us a mole value of 0.0045 moles, which is the same number of moles as calculated for the moles of CO2 produced, making option D the correct option for this question. Question 25. In this question, you should assume air contains 21% oxygen. What is the minimum volume of air required to ensure complete combustion of 10 cm cube of butane gas under room conditions? So the first thing we need to do is write the combustion equation for butane, which would be C4H10 reacting with 6.5 moles of O2, giving us 4 moles of CO2 and 5 moles of H2O. Now, if 10 moles of butane are reacting, the molar ratio of butane to oxygen is 1 is to 6.5. So 10 cm cube of butane is equal to 65 cm cube of oxygen that is required. So now we have obtained the volume of oxygen that is needed. Now we need to find out the minimum volume of air. So since air contains 21% by volume of oxygen, which is 65 cm cube, then 100% of air would contain what volume of, rather, what is the volume of air that would contain 65 cm cube of oxygen? So this would be 100 divided by 21 multiplied by 65. This gives us a volume of 309.52 centimeter cube of air, making option D the correct option for this question.